friends, welcome back to Physics with Ben. This is the continuation of the video series on the marathon calculations on Hooke's law. This is the fourth video series. You'll have to click in the description box below to find the video link for the first series, second series, and third series. And this is the fourth series. It interests you to know that the fourth series is treating a different area in the calculations of Hooke's law. Stay tuned and let's watch to the end. An elastic string of force constants 200 newtons per meter is stretched through 0.8 within its elastic limit. Calculate the energy stored in the string. This is a WAEC question. The first things first we got to do here is to collect your data correctly. So we write that question number 8, the K of the spring is given to be 200 Newton per meters. It's straight through that. And so the extension E is given to be 0.8 meters. And it is within its elastic limit. It means Hooke's law is obeyed. It means F is equal to KE is established. Calculate the energy stored in the spring. In the string or the spring, sorry. Recall that the other video, if you have watched it, the energy stored in the spring is also the same as the work done in stretching the spring. Because work done and energy, they also have the same unit of joules. And so the energy stored in the spring is actually the elastic potential energy of the spring, which is also equal to the work done of the spring in stretching the spring. So we write that, recall. So we write that our W or equals to P, which is the elastic potential energy, is not given. So recall that from W is equals to the work done in stretching an elastic spring, which is also equals to the elastic potential energy is equals to the average force times the extension. In this case, at this point, the average force is 0. I mean, the initial average force is initial force plus final force divided by 2. The work done is times average force times the extension. So what we mean here is that the average force is equal to initial force plus the final force divided by 2. But in this case, the average force is given to be what? F all over 2. We ignore F naught because at this point, nothing is attached to the spring. Nothing is attached to the spring. By the time we start pulling the spring with a mass or with slotted masses, that is when the force will start acting on it. So, average force is 0. So, we write that the W is equal to F all over 2. This is called this equation star times the extension. Call this equation number 1. But recall that F is equal to KE. So we write that this implies that W is equals to KE times E all over 2. So this implies that W is equals to KE squared all over 2. Call this your equation number 2. I wrote these two equations here deliberately because students will be confused. We don't need equation number 1. The reason why we don't need equation number 1 is that the force is not given. And you cannot be finding 2 unknown at the same time in the equation. So equation number 1 is out of the show. So we're gonna use equation number 2. W is equal to KE squared all over 2. So we write that this implies that W is equal to KE squared all over 2. At this point, we substitute correctly. We have K to be equal to 200 Newton. 200 Newton into E into 0.8 squared divided by 2. If we do that correctly, our W is equal to 200 8 squared 0.8 squared. We give us 0.64. So divided by 2. If you evaluate correctly, you have 200 times 0.64. That will give you 128 divided by 2. So W is equal to 128 divided by 2, and that will give you 128 divided by 2. That will give you 64 joules. Therefore, the work done in stretching that string or that spring is given to me 64 joules. 64 joules. As simple as A, B, C. Let's look at the next question. Are we good? Yes, we are good. I hope you are enjoying these calculations. Don't forget to subscribe, to hit the subscription icon and the notification bell so that you can get accurate notification anytime I upload a new content. We want to look at question number 9. When the force of this is applied to the free end of an elastic cord, an extension of this is produced in the cord. Calculate the work done on the cord. Good. We write that from question number 9, our force is given to be 50 Newton, and it was applied to the free end, something like this. Good. Something like this. To the free end of the cord, and the extension, we got an extension E to be 4 cm. That's divided by 1, we got 0.4 meters. Am I correct? Let me confirm that. 4 by 100. 4 by 100. Yeah, I was correct. No, not correct. 0.04 meters. 4 by 100. Yeah, I'm correct now. So it's produced in the cord. Calculate the work done. Work done is not given. So from W is equal to FE all over 2. FE all over 2. We substitute. We want to advise that anytime you are asked to solve a physics question, anywhere, anytime, solve it exactly the way I solve on the board. And you will find yourself mastering physics calculations. And the examiners will be happy when they are marking your scripts. We have this sentence as 2 over 2. This group 1. Therefore, the work done in stretching that spring is 1.0 joules. As simple as A, B, C. We want to look at the next question. Question number 9. Number 10, sorry. So I will not solve question number 10. Question number 10 is also a class activity. see your answers in the comment box. Question number 10 is a class activity. Please, if you are watching my channel, you are subscribed, and you are a student, follow me. Follow my instructions and it will do you good. You watch question number 9, it will help you solve question number 10. It is the same thing, and this is a NECO question. Question number 9 is a WAEC question. Question number 10 is a NECO question. So let's move to the next part of this. And to this we have come to the end of this particular video series. Follow me to the 5th video series where I'll be doing the conclusive parts on these calculations on HOOKE'S law. Don't forget to subscribe, like, comment, and share. Bye bye. See you in the 5th.